morning, everyone, and welcome to the very last session of CHES this year. You know how the best always comes at the end, so it's no wonder we're talking about microarchitectural security today. We have three talks for this final session, and the first talk will be given by Saltanat Firdos, and the title is Tesla Trusted Execution Support for Legacy Embedded Application. The stage is yours.
Hello everyone, very good morning. I'm Saltanat Firdos from the Indian Institute of Technology, Madras. And today I'm going to talk about our work, Tesla. I feel like it's very important for me to clarify that this work has nothing to do with the automotive company Tesla. Yeah, sorry. If you came here expecting that, I'm afraid you may be in the wrong session. So it's just an acronym that we thought would be cool to use. This work is basically about developing a trusted execution environment that can transparently work with legacy applications. So let's start with the motivation. We all know that operating systems are very powerful. They perform a large number of functions in our system. And because of this huge functionality, their code bases have grown very large and complex. For example, Linux has around 30 million lines of code, while Windows has around 50 million lines of code. Because of this huge code base, it's very common for some bugs to go unnoticed. For example, every year, hundreds of vulnerabilities are reported in the Linux kernel. In the year 2024, more than 1,000 CVEs were reported. And this year, until now, already more than 500 vulnerabilities have been reported. Now, these vulnerabilities can be exploited by attackers to compromise the operating system. And since the operating systems run at a higher privilege and they manage all the applications in our system, this may result in all our applications getting compromised. Luckily, we have a solution for this, and the solution is trusted execution environments, which partition an application into secure and non-secure parts and execute the secure parts in an isolated environment, commonly referred to as an enclave, in a way that even the OS is not able to access its contents. So this protects our application from the compromised operating system. For the past 2 decades, we have seen an explosion of TEs, with both industry and academia coming up with different designs, and this innovation is expected to grow in the future. However, most of these TEs require the applications to be redesigned in order to fit their models. They just don't work out of the box with these applications. They require the applications to be written in a specific way for them to be executed inside a TE. But this makes these TEs incompatible with a large number of legacy applications that were written before the concept of TEs. These applications were not written with TEs in mind, so they cannot be executed as such inside a TE, and hence they need to be rewritten if we want to protect them inside a TE. But why do we even care about these applications that were written long back? Well, it's because they are still relevant. For example, a Dell survey in 2016 reported that 70% of the US agencies still use outdated software. The US Government Accountability Office claims that millions of dollars are spent every year to maintain around 50-year-old legacy systems. Even in critical sectors like banking, they still depend on legacy applications, with around 43% of banks and 95% of ATMs using COBOL code that was written decades ago. So the continuous use of legacy applications in critical sectors makes it very essential to think about their protection. And this raises an important question. How can we bring the benefits of TEs to the legacy applications, and what are the challenges associated with this? We'll now look at the challenges of executing the legacy applications inside a TE and how we solve them. The first challenge is that a TE requires the application to be modified. However, legacy applications have complex code bases with little to no documentation available. Moreover, the developers who may have written these applications may no longer be available with the organization that's using this application, and it's not easy for new developers to understand or modify this code. So the takeaway is that it is not easy to modify legacy applications, but TEs demand modification. So this is a challenge that needs to be solved. Another challenge is that a TE by itself does not support system calls. but legacy applications heavily depend on the OS for a large number of system calls. And since the operating system is untrusted, it cannot be executed inside the enclave. So there needs to be some way for the application to invoke system calls. Prior works handle this using two main approaches. One approach is to include the critical OS functionality in the form of a library operating system inside the enclave. However, this increases the size of the trusted computing base, which may result in an increase in the attack surface. Another way to do this is to rely on the native OS for the execution of the system call, but this would require exiting the enclave for every system call. And most of the system calls do require to access some regions of the enclave memory in the form of system calls. So if an application wants to share some data with the OS in the form of a system call, this data would need to be copied from the enclave memory to a memory that the OS can actually access. And this deep copying of system call parameters adds a lot of performance overheads. So we need to think of a way to execute system calls in TEs that does not increase our TCB size and also does not add a lot of performance overheads. One more challenge with executing applications in TEs is the peripheral communication. In order to interact with the device, the application data has to leave the enclave. And most of the existing TEs rely on the operating system for doing so. And this goes against the threat model of TEs because the operating systems are supposed to be untrusted. But those TEs share this data with the operating system to finally share it with the device. Let's consider an example where the application wants to write some secret data to an I/O device. And to do so, it will invoke a system call, and the system call would copy this data into the operating system. And since the operating system is not trusted, it may leak this data to some malicious attacker. So another problem with TEs is that they may leak I/O data, and this is another challenge that needs to be solved. To summarize, in order to execute legacy applications inside TEs, we need to take care of the following requirements. One is that it should not require any modifications in the application. Another is that it should maintain a minimal TCB. System calls should be handled efficiently without adding huge performance overheads. And it should ensure secure I/O communication. With our work, Tesla, we try to solve all these challenges, and let's look at how we do this. So in Tesla, we follow the approach where we put in the entire unmodified application without partitioning or redesigning it inside the enclave, and we rely on the native OS for the execution of system calls. So this solves our first two challenges, not requiring any modifications and maintaining a minimal TCB. Now, for the execution of the system calls, instead of copying the data to an OS accessible memory, we let the OS directly access the data inside the enclave, ensuring that this is the only memory region that the OS is able to access and nothing beyond that. So it's kind of opening a window into the enclave that the OS can access just for the duration of the system call, and we refer to this mechanism as enclave windows. Since this avoids the copying of the parameters, it helps us achieve a better performance and hence helps us efficiently handle the system calls. For secure I/O communication, we ensure that the data always passes through the OS in an encrypted state and is decrypted only in the hardware. So this helps us achieve secure I/O communication. Let's look at how we do all of this in detail. Let's look at the big picture. So to execute an application inside Tesla, we take the unmodified application code and compile it. And the only thing that needs to be done is that this binary needs to be encrypted with some application-specific key. This helps maintain the confidentiality of our application. In order to maintain the integrity, we compute the hashes over the enclave pages. These hashes and the enclave key is encrypted with the public key of the processor. We assume that the processor supports public key cryptography. So these hashes and key are embedded in a separate section in the binary, and the entire binary is loaded by the operating system into the RAM as such, so that the application pages always remain encrypted in the RAM. The only difference at the load time is that when the OS detects this additional section of hashes and keys, it transfers control to a security monitor, which is a software running at a higher privilege and is trusted. The security monitor has access to the private key of the processor and is able to extract these hashes and keys and stores them in a secure region of memory that the OS cannot access. These hashes are used to verify the integrity of the binary pages loaded by the OS on every page fault to ensure that the OS has not tampered with the pages. The key is used to decrypt the enclave pages at runtime for the processor to understand the code and data. To do that, we have implemented a memory encryption engine in hardware. So whenever data and instructions are read from the memory, they pass through this memory encryption engine, get decrypted and then stored in the cache for execution. So all of this maintains the confidentiality of our process, but in order to maintain access control, we have implemented a hardware structure called as an ownership table. So at enclave setup time, each enclave is assigned a unique identifier called the enclave ID or the EID. So ownership table has an entry for each page, and it stores the enclave ID of the enclave to which this page belongs. The core at all times also maintains an enclave ID register which stores the enclave ID of the currently executing enclave. So whenever there's a memory request, the enclave ID of the page is compared to the enclave ID of the currently executing process, and the access is allowed only when the two match. So this is the overall execution of the process in Tesla. We'll now look at how Tesla handles system calls using enclave windows in detail. For the execution of the system call, we make use of the security monitor. We've used RISC-V architecture, so the security monitor is running in machine mode, which is the highest privilege level in RISC-V. So we've modified the hardware to redirect every system call to the security monitor instead of directly going to the operating system. The security monitor identifies the system calls and the system call parameters assigned with it. So let's consider that the application wants to share some data with the operating system in the form of the system call parameter. The security monitor will create a window corresponding to this memory region, and it will register it with the hardware so that the hardware eventually allows the OS to access this specific memory region. It will then transfer control to the operating system, and the operating system can access this memory region for the execution of the system call. Once the system call completes, the control is transferred back to the security monitor, and the security monitor will now close this window and remove OS access to it, and then transfer control back to the application. So since this avoids any copying of the parameters, it actually achieves a better performance. To show the effectiveness of enclave windows, we compare the overheads of the deep copying mechanism with our enclave windows approach using read and write system calls. We considered two approaches, one where the enclave memory is not encrypted, so the only overhead is due to copying of the parameters. In this case, we were able to see that enclave windows result in around 75% improvement in performance. Another approach is where the enclave memory is encrypted, so the parameters need to be decrypted for the OS to understand. That adds much more overheads. In case of deep copying, the parameters are decrypted in software before copying them to the OS accessible memory region. But in case of enclave windows, we perform the decryption in hardware using our memory encryption engine. So in this case, we are able to achieve much more significant performance improvements of around 98%. So this was about how we handle system calls. Now let's look at how we handle the I/O communication. Since the enclave memory remains encrypted at all times, the data that the application wants to share with the device would also be encrypted. So to write data to a device, the application would make a system call and transfer control to the security monitor, which would also see this data in an encrypted form. In order to ensure that the operating system does not tamper with this data, the security monitor will also compute a hash over this data and then transfer control to the operating system. The operating system will also see the data in an encrypted form. And then finally, when the hardware is about to write this data to the device, we'll compute a hash again in the hardware and compare it with the hash computed in the security monitor. Only when the hash is verified, hardware writes the decrypted data to the device. So it maintains both the confidentiality and integrity of the I/O data. Similarly, for an I/O read, when the data is read from the device, it would be encrypted immediately in hardware so that the OS only sees it in an encrypted form. Now, to evaluate Tesla, we implemented it on the Shakti processor, which is a 5-stage in-order RISC-V processor developed by IIT Madras. We've used the RISC-V architecture, so our security monitor runs at the highest privilege, which is the machine mode. We've also synthesized our processor on a Xilinx FPGA board, and we've used Linux-based applications to evaluate its performance. This shows the software overheads of Tesla. We do not make any heavy changes in the operating system. The only change required is at load time to redirect control to the security monitor to extract the hashes and keys from the binary. Most of our software changes lie in the security monitor because it's responsible for handling all the system calls. Currently, we support 80 Linux system calls, and with support for more system calls, the code size of the security monitor will increase, with each system call adding around 3 to 5 lines of code. The security monitor crypto library is responsible for extracting the hashes and the keys, and also for the integrity verification at page faults. An important thing to note here is that we do not require any modifications or addition of code to the user applications, which makes Tesla transparent to legacy applications. In terms of hardware, Tesla adds around 12% increase in the number of LUTs and 24% increase in the number of registers. We've used multiple benchmarks to evaluate the performance of Tesla. Since it's based on RISC-V, we compared its performance to prior RISC-V TEs, Cure and Keystone. And these TEs used the RV8 benchmark to evaluate their performance. So we used the same benchmark to evaluate Tesla's performance and compare it with these two TEs. We were able to see that for most of the benchmarks, Tesla was able to achieve a better performance. And we believe that this is because of the use of enclave windows, because the other two approaches use a deep copying mechanism for system calls. We also used the MI-Bench benchmark to evaluate the performance of Tesla, and also calculated the contributions due to various factors to the overheads, like enclave setup time, system calls, integrity verification, and cache flushing. So at enclave setup time, the only thing that needs to be done is to register the enclave in the security monitor and extract its hashes and key, which does not add a lot of performance overheads. The performance of system calls is also improved with the help of enclave windows, so that overhead is also reduced. However, the major contributor to overheads is the integrity verification. On every page fault, the security monitor verifies the integrity of the page that the OS is loading. And since this is done in software, it adds a lot of overheads. We believe that if this integrity verification can be moved to hardware, it will further increase the performance, improve the performance of Tesla. A thing to note is that we also flush the caches on every context switch for the secure and correct functioning of the processes. And this cache flushing is also adding quite a bit of overheads. In the future, we can think about some better schemes like cache partitioning or something else to protect the enclave code inside the cache. We also use the LM-Bench micro-benchmarking benchmarks to evaluate the performance of Tesla in handling system calls. We compare the deep copying and enclave windows approaches, and we saw that for all the system calls, Tesla performs better due to the use of enclave windows. So to conclude, Tesla provides an easily adoptable solution to work with legacy applications. But even though it has been designed to work with legacy applications, it is not limited to legacy applications. It can work with any unmodified application, and it provides a programmer-agnostic approach. The programmer does not need to write the application in any specific way to make it work with Tesla. It can just work with any application out of the box. The only thing that needs to be done is to encrypt the binary. And Tesla's features like enclave windows and secure I/O communication improve both the security and performance of Tesla. That's it for the presentation. Thank you, and I'd be happy to take any questions now.
Yeah, thank you very much for the presentation. Do we have any questions in the audience?
Thank you for your presentation. I have a quick question. So in your slides, you mentioned that you need to compile the binary and then encrypt it with a key. Do you need a special compilation toolchain, or would it also work with a precompiled binary in case you cannot recompile because you don't have the source code anymore?
No, it can work with the pre-compiled binary. We just need the binary, and we
Okay.
need to encrypt the binary.
Any other questions? If not, then I have a question. So you mentioned that the overhead in hardware is, I think it was about 15%. So what are the most significant changes that contribute to the overhead in hardware?
The first thing is that we've added the memory encryption engine, so that adds a bit of overhead. And then there are some changes in the hardware to redirect the system calls to the security monitor instead of going to the operating system. That's one thing. And for the secure I/O communication also, like for every peripheral, we need to ensure that the hash verification and decryption and encryption is done in hardware. So that adds overheads, and the cache flushing, of course.
Mm-hmm. Okay, thank you. Yeah, we do have time for more questions. Yeah.
Yeah, sorry, just thinking about a question. Since the application is not modified, how your system catch the system call?
So every time an application makes the system call, the hardware typically transfers control to the operating system. We've modified that logic in hardware to transfer control to the security monitor. So it will directly go to the security monitor, and from the security monitor, then it's redirected to the operating system.
Yeah, but the way system calls reach the hardware is need to go through operating system, right?
Sorry, what?
The way system call is reach the hardware, it need to go through the operating system.
I did not get that. Sorry.
Yeah. The application call the system call, it will go through the OS first.
Yeah, but that the program counter is updated in the hardware. So it is that point in the hardware that we have modified. Instead of going to the supervisor trap vector, we update the program counter with the machine mode trap vector.
Okay, thank you.
All right. Do we have any last question?
I was wondering about the overheads, since you mentioned it in terms of percentage. I believe that Shakti is a very small design, so is that fixed, or if I have a larger processor, would it amortize? I mean, the overheads on the hardware.
Yeah,
are they fixed
compared to a bigger processor, the overheads will not be as large, I believe.
Okay, so it's like a fixed engine
Yeah.
as such. Okay, thanks.
All right. Then I would say let's thank the speaker again.
Thank you very much.
And then we come to our second talk of the day, which will be given by Omar Jakas. And the title is VIMA, a privacy-preserving integrity measurement architecture for containerized environments.
Testing. Okay. Thank you guys so much. So my name is Omar. I am a PhD student at the University of Queensland, and I want to present our work, which is, VIMA, a privacy-preserving integrity measurement architecture for containerized environments, extending hardware root of trust to containerized environments without compromising privacy, using Merkle trees and zero-knowledge proofs. So this is a quick outline of what we'll be discussing. So I want to start by talking about hardware root of trust. I'm sure that most of you know what hardware root of trust is, but for those of you that do not know, the concept comes from the concept of hardware is more trustworthy than the software because it's harder to subvert. So you can actually place your trust in hardware, and then basically from the hardware you can measure the overlying software layer, trust it, and then this software will measure all the way until you reach your application that needs to be trusted. You can have boot and firmware security, remote attestation, secret protection, and zero trust gates. So in modern computing, The most used module for this type of root of trust is, I'm sure that you guys know, is the TPM, which is a tamper-resistant hardware component that is embedded in the motherboard and provides cryptographic operations. And it also has specific registers called the platform configuration registers that allows you to store the measurements in the hardware so that you can have the hardware root of trust. The measurements are stored using a PCR extend function. It also allows you to sign attestation quotes for your remote attestation and sealing and unsealing along with other cryptographic functions using the crypto engine. Yes, so the TPM is great, but it can only do so much without the overlying software framework that allows it to extend its functionality. And the best framework that exists for extending the TPM functionality in modern computing is the Linux Integrity Measurement Architecture, which was proposed by a paper accepted to Usenix in 2004, and then it was made in the mainstream Linux kernel in 2009. And it's basically just extending the TPM for continuous runtime integrity measurement, verification, and attestation. So you can have continuous verification of your TCP, which in this case is the entire Linux kernel. So it works using the following operations. So first of all, it detects a file execution request using the Linux security module, hooks, and intercepts this request, talks to the integrity measurement architecture to measure it using the agent, and then calculates this hash, and then this hash is first extended to a measurement list, which is a measurement in the software, and then extended using the extend operation of the TPM to the TPM PCR. So this is a high-level architecture of how it works. Basically, as you guys see, there's the hardware, there's the kernel space, and the user space all working together. A file that exists in the user space will trigger a hook of a file mmap, which is mapping the file in memory. And then it will trigger the integrity measurement architecture to measure and store it and extend it to the TCP. And you have an attestation service running in user space that allows you to do the remote attestation. So yeah, this is basically how the integrity measurement architecture works. But as you guys know, that it was published a long time ago, over 15 years ago, and modern computing has changed a lot throughout this period. With the rise of like cloud computing and those cloud native deployments these days, the paradigm of computing has changed from traditional monolithic single application deployment, where everything is bundled up in one big monolithic VM, to microservice architectures, where you have different services running together and talking to each other, having their own software stacks. Microservice environments, orchestration environments using Kubernetes, and all of these, like basically the heart and soul of those deployments is not just cloud and virtualization, it's actually also containerization, which is basically the ability to bundle up those services into executable components that can run independently anywhere as long as they have their container runtime. So basically, this is a zoomed-in look of how we go from single monolithic application to containerized-based microservice environment deployment, where you have multiple containers running in user space. They are being segmented or hypervised by a container runtime, all of them sharing one Linux kernel running on either the hardware or a virtual machine or a hypervisor. But as you guys see, or as you guys already know, containers share the same kernel, and that exposes them to a shared attack surface where in order to trust one container, you have to trust the kernel not to be exploited, and you also have to trust the other containers running inside the same environment because of the weak isolation and the multiple kernel level dependencies that they require. So now the question is, can we extend functionalities, can we extend hardware root of trust to containerized environments today? And can we do that securely? So what if we try to extend the integrity measurement architecture to containerized environments? So we tried to do that, and we ended up with 3 security challenges. So the first one is limited container autonomy. So the kernel is a monolithic code base. So that means that they have one centralized Linux security module that keeps the security of the entire system together. However, in containers might run different things and have different policies. And when we talk about policies, we're talking about how we're measuring them and what are we measuring. And for different containers, what we are measuring and how we are measuring them differs a lot. The second thing is privacy concern, and actually privacy and granular verification are very linked. Basically, the idea is if you want to verify one container, you have to verify this container against the entire system, which includes all of the containers and the kernel and everything else. That gives you a lot of privacy concerns because you expose all of the files, all of the container in order to verify one container. And also, in order to verify one container, you have to actually verify everything to make sure that everything works in order to verify this one container. So basically, the root problem of that when we were investigating is that there's a concept called user space fiction. And user space fictions are containers. So basically, from the kernel perspective, containers do not exist. Containers are just made up in user space. From the container perspective, containers are just processes or collection of processes being collected by namespaces. So there's no one container object that exists in the kernel that you can track and verify. So the concept of user space fiction has existed, and this problem has been worked on in the literature. However, most of the techniques, they all try to either virtualize the integrity measurement architecture for different containers, split them, or use namespaces to piggyback off different namespaces to do that. However, each approach either breaks the unified integrity view, so by splitting the IMA, you lose the integrity view of the entire system in order to have a view of the container. In order to have this integrity view, you have to add duplication in terms of verifying the container and then verifying the system separately. That also produces a lot of hardware integration complexity when you want to integrate those measurements into the TPM. And also when you want to work with the IMA namespace, the solution is to piggyback off of user namespace, and piggybacking off of that introduces a lot of vulnerability in terms of privilege escalation, because any changes in this namespace, any vulnerability that you introduce allows you to basically have privilege escalation in Linux. So that's not good. So this is why we introduced VIMA, which allows us to extend hardware root of trust to containers without sacrificing autonomy, privacy, or verification. And to be honest, the architecture for VIMA is straightforward and simple. What we use is we use a two-tiered tree architecture where we have a monolithic root data structure that is on the entire monolithic kernel. And then for each container, we have a dedicated Merkle tree that is encapsulated by its Merkle root. So for files that are running inside containers that are tracked by the given container Merkle tree, this is encapsulated into the root, and then the root is cryptographically linked to the system by being a leaf inside the bigger Merkle, monolithic Merkle tree. So we use Merkle trees, and we use this type of two-tree layer because first, Merkle trees allows us to encapsulate integrity inside the root. So that's very good. But also, The reason that we did a two-tree architecture is because we want update on the container level, not to affect the entire system. So if you want to update just the container, you can update just the root and then put it into the monolithic Merkle root without updating the entire data structure of the entire system, which is costly. And also, you are able, because of this type of data structure, you're able also to bind metadata and other types of integrity verification primitives. So with our architecture, we were definitely able to solve those three gaps in order for container autonomy. Since the integrity is encapsulated into the Merkle root, we can verify the integrity of containers separately, which allows them to have different policies. We also are able to have privacy preservation because of two things. First of all, as I said, everything is encapsulated into the Merkle root. And also we can use zero knowledge and proof of inclusion to attest that a given file or a given container exists in the system and is verified without actually having access to everything that is in the system. And also we are able to use Merkle proof to do a streamlined integrity verification process. So we were able also to bypass all of the pitfalls of the other approaches because the use of a two-tree architecture allowed us to still have a unified view of the Merkle tree and the individual containers. Simple hardware integration where you just, since everything is encapsulated in one Merkle root, we can add this into the TPM using the extend operation with no redundancies. And also the logic is non-intrusive. I'll show how it's non-intrusive in a bit, and it's also simple. So we don't have to piggyback off of user space, user namespace, and we don't have to do any intrusive architecture changes into the IMA. So basically, this is how our remote attestation would look like. So we have the verifier and the prover, and in order for the verifier to prove, the prover to prove for the verifier that a given file or a given container exists in the system, you basically, from the constructed Merkle trees, you can produce a ZK snark circuit. And then the proof of this circuit coupled with the Merkle root would be signed by the TPM and then returned to the verifier as the attestation data. So this is also a high-level architecture of what we did in terms of changes. As you guys can see, the Merkle tree for each container is bound to the system-wide Merkle tree, and then only the root is extended, and then you can have a zero-knowledge attestation service in the user space. So for the implementation, we had a lot of challenges in that. One of the biggest challenges was, all right, like if we have the problem of user space fiction, how can we identify containers? And how can we identify it in a way that is good with our type of data structure? And what we realize is that containers are segregated, or the virtualization primitive that is used in the container in order to virtualize or containerize application is namespaces. So basically a set of processes share a set of namespaces are basically seen as a container from user space. So, but those are very different. You can have different isolation on the network layer, on the user layer, on the file system layer, on different layers. So we did an assumption that a collection of processes who have at least 3 common namespaces can be considered containers. So there's overlap, but that is actually helpful when it comes to shared files and stuff like that. Also, there was performance in like moving from a measurement list to a Merkle tree in terms of updating this data structure. So this is more of an engineering work, but we did a lot of caching and a lot of optimization in terms of the data structure in order to have good performance. And also we realized that what we can do is that we can leave the Linux kernel as is, we can leave the IMA as is, and we can just piggyback off of that in a non-intrusive way using the LSM hooks. So basically, the Linux security module exposes specific API, let's say functions, that you can basically get a lot of information of and extend to them. So that's what we did, and it's basically very simple to insert it and then remove it whenever you want. So basically, the code base was developed by us, and it's approximately 10K lines of code, which includes everything from the lifecycle management to the IMA integration and the Merkle proofs and stuff like that. It was the setup or the experiment was just done on an Ubuntu server. But for the implementation, what we did is we modularized it a bit because we split the the control plane from the data plane so that you can have a pluggable backend in terms of the data structure. So going back to containers have different requirements, and for the decentralization, you need to have different data structure, for example. So we have a pluggable backend that allows you to configure the different caching algorithm that you want to use, and also the different data structures. Yeah, and another thing is that what we did inside the code is that given our namespace assumption, there are files that exist outside of the container, but we treat them as a container, as the host container that is also linked to the monolithic tree. That was a design decision that allowed us to treat everything as containers, and everything can be inserted into one monolithic data structure. So yeah, these are some of the evaluations that we did, and this is basically evaluating the performance of the Merkle tree and the different optimization that we did in the caching. So we did a lot of stuff such as batching and pruning, and a lot of different caching techniques to make the process as good as the original Linux integrity measurement architecture measurement list. And we also tested a lot of different real-world containers. So we tested a lot of AI containers, PyTorch, OpenVINO, and others, much others. And databases, Redis, SQLite, MongoDB, and light HTTPD, Terrific or Traffic, Apache, and Nginx. And we got good results at the end after our various iteration of optimization. So I just want to finish by talking about our use cases. So we were able to prove that Weimar has a lot of applicability when it comes to multiple environments. This includes enterprise deployments, where you want to verify a container that is given to a given employee. Also in multi-tenant environments, so think SaaS-based environment where a lot of containers are used for different tasks, but also for confidential and trusted execution environment. So the first one we thought of is that when you want to use, so there's two different trusted execution environment types. There's the VM level types where like AMD SEV or Intel TDX, where you have the entire Linux as a trusted execution environment. So for that, in order to streamline the deployment of end-to-end application using confidential containers, let's say, you need to have end-to-end integrity verification, and the granularity, specifically the granularity of Weimar, allows you to have this end-to-end verification at the container level while verifying that the entire system is correct. And also on the process level TTE, so think Intel SGX. So currently the TCB in those type of environments are immutable, so they do not change. And one of the reasons why those TCBs do not change is because of you don't want to change the TCB for integrity verification purposes, because once the TCB changed, the integrity is lost. However, not changing the TCB, aside from like encrypting the code base before loading it, if you want to load it into SGX, you open yourself to attacks called pre-enclave attacks, where you can see the code before it's loaded into the SGX. But with continuous runtime integrity verification, you can load, if we're assuming that we have a mutable TCB that we can verify, we can load the container in the trusted execution environment at runtime, and then put the logic of verification inside the trusted execution environment, and only provide the proof to the untrusted host. So yeah, and I was going to say another thing, but I forgot. But yeah, basically this is it, and yep, thank you.
Thank you very much. Do we have any questions? So I will start. What would you think would it take to get this technique into current kernels? So could you imagine your technique being implemented into the current Linux kernel, or are there any challenges that come with that?
Yes, excellent question. Thank you for that. So yep. The good thing about our implementation is, as we said, it's not non-intrusive, so it's a kernel module that can be injected, and we are in the process of open sourcing it. We submitted it as an artifact for this conference, and hopefully what we want to do is we can get adoption to use it, because it's very simple. You don't have to do a lot of things to get it working. And yeah, I don't think it will, I think it's already like used. Like, I have a startup and I'm currently using it as one of the things, if that makes sense.
Oh, yeah, that's very nice. So
yeah, thank you.
I think it's a good thing to have in the kernel, and a good capability. Yeah. So last chance. Do we have any other questions from the audience? That does not seem to be the case. So then let's thank the speaker again.
Thank you. Thank you.
And then we come to our final talk, and the paper is called Optimized One-Dimensional Ski Sign Verification on Intel and Cortex M4. And I will do my very best with the pronunciation. So the speaker is Jorge Emanuel Chavez Saab. I hope that was good. Yeah, that's good. So the stage is yours.
Thank you. So hello guys, congratulations, you made it to the last talk of the conference. So I'm here to talk about optimizations that we did to one-dimensional ski sign. This was accepted to CHES about a year ago. I don't know if you have been following ski sign, but if you do, you'll know that a lot of things have happened in the last year. So this work has aged a little bit, I'm not gonna lie, but I think it's still gonna be worth your time. So SkiSign is one of the 14 candidates that made it to round 2 of the NIST additional post-quantum signature standardization process. And it is the only one based on isogenes. It has the main advantage that it has by far the best combination of public keys and signatures out of any post-quantum scheme. And it also has a reasonable verification time, but its disadvantage is its signing performance. It has been getting a bit better, especially in round 2, but still not the best. So because of this, SkiSign is going to have very niche applications in scenarios where you only have to generate a signature once and verify it many times, such as certificates and blockchains, and also for embedded devices that only want to do verification, like IoT devices, because they're not going to be very performant, and also they might not have a lot of memory to store big keys and signatures. So this is kind of the developments that have happened recently. I just want to call your attention to this part, which is really where the revolution started with the 2D variants of SkiSign. So these 2D techniques are the same that were used to break SIDH back in the time, but through a twist of fate, they are now being used constructively to improve SkiSign. So we had 3 papers that came out almost simultaneously, nicknamed SkiSign to the West, SkiSign to the East, and Ski Prime. And they had a surprising speed up of factor 15 in signing, and then the verification got a little bit more complex because it had to do 2D isogenies. However, they claim that it was still even faster than the 1D verification. Although it is worth noticing, this is comparing against the NIST round submission, which, to be honest, wasn't particularly well optimized. Shortly after, Onuki and Nakagawa showed that you can do kind of a hybrid scheme where the signing gets sped up by the 2D techniques, but the verification is still 1D. So that is where our work comes in. We were wondering if doing 1D verification can still be competitive if we optimize it well enough. So I'm going to do a little bit of background. An isogeny is just a rational map between elliptic curves. And in isogeny-based crypto, we are concerned with the supersingular isogeny problem, which is given two supersingular curves to find an isogeny between them. This is thought to be a hard problem, even for a quantum computer, but it has kind of a backdoor. If you know the endomorphism ring of both curves, then the isogeny is actually easy to find. I'm not going into details about the endomorphism ring, but basically there are two rules. There is a curve E0 for which we always know the endomorphism ring. And then if I tell you a path from E0 to another curve, you can use that path to find out the endomorphism ring of the other curve as well. However, if I just tell you a curve somewhere in the middle of the graph, but I do not tell you the path to it, then you have no way of knowing the endomorphism ring. So with this in mind, ski sign is basically based on a zero-knowledge proof of knowledge, where the secret is the knowledge of an isogeny, which translates into a knowledge of the endomorphism ring of a curve. And you demonstrate this knowledge through your ability to solve the supersingular isogeny problem. So concretely, what you do is this. You start with a curve EA, which is your public key, and you do a commitment isogeny to another curve that is E1. Then the verifier comes, and based on your commitment, it tells you another isogeny that takes you to a challenge curve E2. And then the task of the prover, or the signer, is to produce an isogeny between its curve and the challenge curve. So that is basically how ski sign works. In terms of parameters, we work over a quadratic field, where the size of the prime is determined by the security parameter. And originally, we wanted p squared plus 1 to have a very specific form. Basically, we wanted it to be as smooth as possible. So you have 2 to the f, 3 to the g, and then some factor t, which is supposed to have larger factors, but which are still as smooth as possible. This t is only used for efficient isogenies in the commitment isogenies. So it is not used in verification at all. It is only used in signing. However, it is still competing for space in the factorization here. So the beauty of 2D techniques is that they allow the evaluation of arbitrary degree isogenies under certain conditions. Therefore, you do not need the isogeny to have a smooth degree. And that means that you actually do not have any need for t here. So when these 2D papers came out, they proposed moving to a brand new prime, which is essentially just a power of 2 with a very tiny cofactor. And we call this prime P248. So what Onuki and Nakagawa show later is that with this kind of hybrid scheme, where signing is 2D but verification is 1D, that means that 1D verification can also be made to work with this prime, which is a lot better, rather than this prime. This prime is better not only because it's going to allow you to do 2 isogenies very fast, it's also going to accelerate the entire field arithmetic because it is extremely Montgomery friendly. So that is where we came in. We were wondering if an optimized 1D verification using this prime can be as fast as the 2D results. Because at this time, people were kind of ready to move on to 2D, but we realized we didn't really have a baseline for how good 1D verification could possibly be. And also, can we even make it fit inside the Cortex-M4? Because I have been saying this is probably one of the better use cases for ski sign. However, it is a very complex scheme, and no one had ever implemented it for such an embedded device. So that is our approach. We optimize 1D verification as much as possible. We do not focus on signing. And we use for concreteness, we focus on level 1, and we use the same prime as the 2D papers. So this is nice not only because it will give us the best possible performance, but also it allows for a direct comparison with them. And then we made a large implementation effort to kind of update the ski sign library and target the Cortex-M4. All right, so the first thing that we did in trying to compare 1D versus 2D is kind of a napkin calculation to figure out what the cost of the respective isogenies would be. So here we have the cost of the isogenies in 1D and 2D. I'm going to skip over the details for the sake of time. But end of the story, we found that 2D was in fact expected to be slightly faster than 1D, although not by a factor of 4 as they were claiming. So this is already a win for 2D. However, this is taking into account only the cost of the isogenies themselves, and we have a few other costs in the protocol. So you may know in 1D, an isogeny is represented by a kernel point, K. So you can put this point in the signature, and you get what we call uncompressed isogenies, which are kind of fast, but the point K is going to take a lot of space in the signature. On the other hand, you have compressed signatures, where the kernel point is encoded as a scalar, which is lowercase k, and it is such that big K equals P plus little kq, where P and Q are just some kind of canonical basis that you have a deterministic way of computing. So this is this produces shorter signatures because now you only have to put this little k in the signature. However, it incurs additional costs in the verification since you still have to reconstruct this basis and then compute P plus kq, which is something called a Montgomery ladder, and it's rather expensive. So these are the two routines that we focused on improving for 1D. Starting with basis sampling, the way this used to work, you just had to grab a random point and then double it repeatedly to check that it had the right order. And if it didn't, you had to move on to another point and start doubling again and so on. This was extremely expensive, but then there was a paper called Apresky, which came up with something they called smart sampling. And this essentially eliminates the entire cost of these doublings. Rather than doing doublings, you just have to do some quadratic reciprocity checks to check that the point has the right order. So this is much, much faster. However, it is worth noting it still had one main cost, which is computing what we call alpha. Alpha here is a root of this polynomial, which corresponds to the elliptic curve. In other words, you can think of it as the x-coordinate of a point of order 2. And computing this requires a square root. So, still faster than the older method, but it has a bit of overhead. So we made a few changes to the protocol to avoid this overhead. The first one is, if you think about the public key, it consists of a curve. Usually it is specified by the Montgomery A coefficient, but we figured out we can just specify it by alpha itself. So this doesn't change anything because you can always recover A from alpha very easily. However, the converse is not true. So we have the signer compute alpha so that the verifier doesn't have to. And the same applies to E1. E1 is the commitment curve, and it goes in the signature. So instead of putting A in the signature, we put alpha. Now, one thing I have not gone over is that this response isogeny, you actually have to compute it in blocks because its degree is around 2 to the 1,000. If you remember the prime that I showed you, the power of 2 is 2 to the 248. So that means you cannot compute this entire isogeny in one shot. You have to do at least 4 blocks. And after each block, you have to stop and sample a new basis. So that means we also have to compute alpha in each of these curves. And these curves are only known at runtime, so we have no way of predicting their alpha. However, we do another trick to prevent this. So you may know when you're doing an isogeny of degree 2 to the f, you usually split this into a chain of isogenies of degree 2. So you start with a kernel point of order 2 to the f, and when you push it one step, you have a point of order 2 to the f minus 1, then 2 to the f minus 2, and so on. So before you're taking the very last isogeny here, you have a point of order 2. And if you remember, I told you a point of order 2, its x-coordinate is precisely alpha. So in this curve, before I get to the end, I already have alpha computed for me. So what we propose is just end the chain early, and at this point, just use this alpha to compute a brand new basis and start the next block from here. So we're doing slightly smaller blocks of size f minus 1 rather than f, but this does not affect anything. And this way, we don't ever have to compute alpha, so no square roots at all. The next contribution that we have is called smart hashing. So we need, in order to compute the challenge, we have to have a way to hash into a kernel point that represents an isogeny. The way this used to work is you had to sample a basis P and Q, hash to a scalar, and then compute P plus KQ. We had an improvement that is based on the same ideas as the smart sampling, and the relevant result is this one. Basically, if you have a point in a curve where the x-coordinate is not a square, it is automatically guaranteed to have the maximum power of 2 torsion in its order. So basically, what this means is you just have to sample an x-coordinate that is not a square, and then check if it is in the curve. If it is in the curve, then you're done. Otherwise, you just keep sampling. And of course, the way you sample a non-square is just sample any number, square it, and multiply it by a non-square. So this algorithm to the right, it might look longer than the one to the left. However, sampling bases and the Montgomery ladder are really expensive, whereas here we're not doing any elliptic curve operations at all. So this is practically free in the protocol. And lastly, the last contribution that we have is proposing the use of parallelism for verification. So if you think about it, there are 5 different isogenies that the verifier needs to compute, which is 1 for the challenge and 4 for the response. So if you just have to compute 5 independent isogenies, why not do them concurrently? The only caveat here is you cannot start working on an isogeny unless you know its domain. So that means you are stuck with computing these ones sequentially, unless you put these intermediate curves in the signature so that the verifier can start working on them immediately. So here I have kind of linearized the triangle that I have just showed you. And the curves in blue are the ones that you would have to put in the signature in kind of the naive way. So this would require having 5 curves in the signature. And that pretty much triples your signature size. So it's not very desirable. However, we figured out that you can change the direction of some of these arrows. So some of these isogenies, you're not verifying them in the conventional direction, but you're rather verifying the dual. And the reason that this is nice is, if you remember, you only have to know the domain of the isogeny, not the codomain. So if you arrange the arrows in this way, now it's only 2 curves that you have to put in the signature. And so this increases your signature size just from 157 bytes to 285. All right, so these are the results that we got kind of on a high-performance CPU. The first row here is the NIST-1 submission, and the second one is the 2D West paper. So you can see here there is this acceleration of 4 that is very impressive, which they were claiming. However, we found that by just optimizing the 1D verification as much as possible, we managed to obtain pretty much the same acceleration as they did. And then if you move on to the other variants, especially with parallelism, we can get even a factor of 25. And we're doing verification in SkiSign in just over 1 million clock cycles. Now, I would love it for the story to end here, but I do have to tell you the whole story, which is for round 2, we did decide to go for 2D rather than 1D. And turns out 2D also had a few optimizations left to do. So after optimizing 2D as much as possible as well, for the compressed signatures, we managed to drop this to just 5.1 million cycles compared to the 8.55 here. So a little bit of a negative result. This was before this paper was after this paper was accepted. We are now rather confident that 2D verification is indeed faster than 1D. However, we also have all these variants with 1D, especially the parallel ones, which might be interesting in some scenarios. And you might be thinking, well, it's not really fair to compare something that is using parallelism versus something that is not. However, we argue that because in 1D you're doing the isogeny in 4 blocks, it is kind of naturally parallelizable, which is not the case in 2D. All right, so now I would like to talk about our implementations efforts on the library itself and how we took it to the Cortex-M4. So like I said, SkiSign's characteristics make it a very good candidate for doing verification in embedded devices. However, the library from the first round had several obstacles. There was no option for a verification-only build. You always had to compile the entire thing, which was problematic because there's no way that signing would ever work or even fit in the Cortex-M4. We also had heavy use of dynamic memory. It only worked in 64-bit systems. And also, if you wanted to optimize field arithmetic, we only had an option for the Broadwell architecture. Outside of that, you were stuck with fiat crypto, which it's not terrible, but also not the best. And it also had a dependency on GMP, which again uses dynamic memory, and it's not supported by the Cortex-M4. So starting with the field arithmetic, this is very important because the entirety of verification is pretty much 100% field arithmetic. So it's very important to get this right in terms of the cost. So we adopted 3 new options. For portability, we actually replaced fiat crypto with Moderate. This is a generator by Michael Scott. and it still produces generic C code, so it's just a replacement for fiat crypto. However, it uses an unsaturated representation, and we found that it is much better at exploiting the Montgomery-friendly form of the prime. And in some testing, we found that it could be up to 2 times faster than fiat crypto. And then specifically targeting the Cortex-M4, we have an option for M4 Modarit. This is a generator that was inspired on Modarit, but it has custom optimizations and assembly code specifically targeting the Cortex-M4. And that was actually presented in a paper right here in CHES 25, that was on Tuesday. So if you did not go to that talk and you find this interested, please check that paper. And then for high-end Intel devices, we also have an updated version of the Broadwell assembly code that was kindly provided by Patrick Longa. Moving on to the quadratic field, there are 3 specific operations that we targeted. They were the square root, the inversion, and the quadratic residuosity. These are basically used in the basis sampling and also the smart hash. So they are, if you remember, these are the main costs outside of the bare isogeny computation. So they are important. In the original version, all 3 of them were implemented through exponentiation, which is not great. So we just kind of updated all of this to represent the current state of the art. All right, so for the library, we restructured the entire library, and we added a verification-only build option. And to this build option, we added support for the new P248 prime. However, we still support all the primes from the original round 1 submission, and those benefit from all the improvements as long as they are improvements that do not break backwards compatibility. So we still retain an option to be backwards compatible with round 1. And you can find that library here. We also made a full 32-bit port of SkiSign, and we integrated it to a branch of PQM4 for doing our benchmarks on the Cortex-M4, where we had to do a dummy signing, because we're only interested in getting numbers for verification. You can find that in this other link. So these are our results for benchmarking in the Cortex-M4. The first row is the NIST submission only with minimal changes to make it work in 32 bits. The second row represents the optimizations that you can do without breaking compatibility with the original parameters, and that gives us an acceleration of 1.5. But if you use the new prime and you bring together all the optimizations that I talked about, we get an acceleration factor of 4.73. So for sure, the original NIST submission was rather far from being fully optimized. And this is only used in fiat crypto, but if you move on to Modarit, which is still fully portable C, you get an acceleration factor of 13. And then the one that targets the Cortex-M4 specifically, you get an acceleration factor of almost 20, which is quite impressive. And we're doing verification on the Cortex-M4 in under 100 million cycles. All right, so to conclude, we found that 1D verification is comparable in performance with 2D. Although if you take into account signing, it might not be worth considering so much. However, we do get excellent acceleration for 1D using a small degree of parallelism. And then on the other hand, SkiSign verification does fit in the Cortex-M4, and it gives reasonable performance results. And finally, I would like to say, even though for round 2 of the SkiSign submission, we did go with 2D rather than 1D, a lot of the changes that we made to the library actually made their way to this submission in 2D. So that's still kind of a nice little legacy that this work still has on that submission. So that is the end of the talk. Thank you. And I realized this had nothing to do with microarchitectural security. Here are some stock images for you. Thank you.
Thank you very much for your presentation. Do we have any questions from the audience?
Thank you for the presentation. I have a few questions. So regarding the smart hashing that you have proposed, you are hashing the public key message counter altogether. So is it also possible to say hash the message previously, like a pre-hashed version like used in MLDSA, and then you feed that into the smart hashing rather than the entire message itself? Would that also work?
Let me see if I understand. So hashing the message first?
Yeah, so you hash the message first and say get a 256-bit hash output, and that you send into your smart hashing instead of the entire message itself.
Okay, I see what. Yeah, you can do that, yeah, for sure.
Okay.
It's just, I mean, the protocol as it's defined now, you feed the entire message, but yeah.
Okay. And regarding the counter, so for different public keys, different messages, you will have different values of counter where the loop will break.
This one,
yeah? Yes, exactly. So does that have any security issues, or this is verification only with public values, so there is no side channel?
Yeah, these are fully public values. Basically the idea behind this is when I'm standing in a corp, you and I get to some agreement of how to encode the points. So you're going to give me a scalar rather than a point itself. But this agreement, this basis, it can be fully public. It is not secret information at all.
Okay. And one last question. So now that the SkiSign team has gone with the 2D version, do you see any application scenarios where the 1D would still be useful?
Yeah, I mean, things have been moving quite fast for isogeny-based crypto in general. Just the sheer fact that we, after so many changes, 1D and 2D ended up landing fairly close together, like in the same order of magnitude. So who knows? I mean, we could be like just one breakthrough away from things turning around, right? Currently, I think it is clear that 2D right now is the way to go, but I think it's still worth studying.
Thank you.
Yep.
We would have time for one more question, if there is any. That does not seem to be the case, so then let's thank the speaker again.
Thank you.